All right. So today the big goal is to handle what we call alternating series. Now, an alternating series is something of the form this. Now, whether that's an n or an n minus one isn't all that important. A lot of the authors like to put an n minus one, so the first term is positive and so on. That's really not important because an can be positive or negative. But the way I would look at this right here would be negative a1 plus a2 minus a3 plus a4 forever and ever and ever. I alternate signs between them. Now, the crazy thing is, if I have terms that are getting smaller and the signs alternate, I'm going to have, in a sense, everything's kind of canceling each other out as it goes. So meaning, if I'm alternating, first of all, my sum should be smaller than if I'm not, because again, you have this huge canceling effect. But the best part is, I can have a series that does not necessarily converge, but if my terms are getting smaller and I'm doing this, when I'm adding them together, they're usually going to add up to a very small finite amount. So I'm going to go ahead and prove that. And so an alternating series might converge where the non-alternating series didn't. So we create a scenario where we might get many more things to give us answers than before. So I'm going to start with a couple of really simple assumptions. And usually when you have an alternating series, you quite literally mean it, every single term changes signs. You don't have a couple of positives followed by a couple of negatives and so on. So let's start with a simple condition. Okay, I have something an, and we're going to start with the following, that the terms are going to be getting smaller as I go, no matter what. So that a1 is greater than or equal to a2 is greater than or equal to a3, right? And forever and ever and ever, the terms, they can stay the same or they can get smaller, but they never get bigger, okay? So all my terms are getting smaller, 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 smaller. So what I'd like to do is I would like to calculate the sum of the first 2n terms. And that's by design. I want an even number of terms. If I ask to calculate the sum of the first 2n terms with this, so remember now, we have an alternating series. So here's the way I'm going to set this one up. I'm going to set this one up so it's -1 to the n minus 1. I'm going to set it up so that the first term is positive. I'm going to do that for a reason. So that means that this is going to be a1 minus a2 plus a3 minus a4 and so on. Okay, I'm deliberately doing that. You say, well, what if the first term's negative? Well, then I can factor a -1 out of the quantity. It doesn't change anything. Okay, so what is the sum of the first 2n terms? Well, that means I'm going to end at, let's see, looks like the negative is in front of the even term. So my last term would be a 2n. Does that make sense? It'd be minus. So what I'm going to do is I'm going to group them. Now stare at that for a moment. Tell me if that's true. I have 2n terms. 2n would be an even number. So a1 minus a2, a3 minus a4. So the even number is always the second term. It's always being subtracted. Okay, this is the sum of the first 2n terms. But based on that statement right there, can't I say, if every term is staying the same or getting smaller, wouldn't this therefore be, oops, put that in the wrong spot, sorry. Wouldn't that be greater than or equal to 0? And wouldn't that be greater than or equal to 0? Now, does that make sense? Every single one of these differences is greater than or equal to 0. It would only equal 0 if the term stayed the same. It's bigger than 0 if the term got smaller. I'm going to add up all of these quantities, so I think it's safe to say that this is greater than or equal to 0. Now, infinity is greater than 0 also, so I haven't proved anything except that if I start with the first term being positive and my terms are getting smaller, then an even number of terms has to be greater than or equal to 0. The only way it could equal 0 is if all the terms are the same. Okay, and that's really not going to happen very often. Now I want to do the same thing again, but this time I'm going to group them slightly differently. Now I want to group them this way. Okay, I want to now group them the next pair over and over again. I want to pull out the first term, and I want to pull out, let's see, which color do I want to use? So now what I've got, I want to write this as A1 minus A2 minus A3. I'm factoring the negative out of those two, minus A4 minus A5. You with me so far? Minus dot, 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 minus A2n minus 2 minus A2n minus 1, and then finally minus A2n. Well, just like before, that's greater than or equal to 0. That's greater than or equal to 0. That's greater than or equal to 0. And that last term, of course, is greater than or equal to 0. I'm starting with A1, and then I'm subtracting perhaps a positive amount, and then I'm subtracting another positive amount, and then I'm subtracting another I'm subtracting positive amounts from A1.
Professor.
Yeah.
So you're pulling out a negative from the A2 plus A3. So wouldn't that be a positive up front?
Distribute the negative.
Oh my God. Okay.
Yeah. That's it.
Very well.
Why am I doing that? Because I'm bounding my sum. So here's what we've got so far. This, again, starting only with this assumption that my terms are staying the same or getting smaller. In reality, they're getting smaller. It would be really hard to have any form of a series where terms stayed the same. No, they get smaller. But we're saying stay the same or get smaller. So it's going like this. If I add up the first two n terms, I just proved that it's greater than or equal to 0. Now I regrouped them. So when I added up the two n terms, what do I get? A1 minus a whole bunch of positive stuff. So in simple English, that means my S2n has to be less than or equal to A1, doesn't it? Because I'm going A1 minus a positive quantity, minus a positive quantity, minus a positive quantity. And at worst, I'm subtracting 0. Huh. I've got S2n is greater than or equal to 0, but less than or equal to the first term. I can now say with certainty, this is between 0 and the first term. Whoa. The sum of the first two n terms is between 0 and the first term. Remember what I said? I said if the terms are getting smaller and they're alternating in sign, it's as if they're kind of all canceling each other out. This is the proof right here. We just proved this. So now let's go back to the original series. And this is really cool. So my original series, which I'm going to start with a positive term, just to make it easier to explain. Oops, and this is the infinite sum. So remember, the infinite sum is the limit as n goes to infinity of the nth partial sum. But my nth partial sum is between two constants. So if I said the limit as n goes to infinity of 0 is less than or equal to the limit as n goes to infinity of Sn, and that's less than or equal to the limit as n goes to infinity of A1, that's just the squeeze theorem. But the quantity on the left is 0. The quantity in the middle is the infinite sum because it's the limit, and the quantity on the right, oops. Oh my goodness. We have just shown that in an alternating series where the terms are getting smaller, that's the key, that the alternating series is between 0 and the first term. Whoa. And by the way, that is extremely powerful. That means we might get convergence when we would not have otherwise. So let's see how that would work. So the only condition I had to satisfy was that my terms are getting smaller. Well, what if my terms are not approaching 0, by the way? Remember, the nth term test is still critical. If you have a series and your terms are not approaching 0, your series is going to diverge, whether it alternates or not. If your terms are not approaching zero, it's like you're adding an infinite number of non-zero numbers up, and no. So failing the nth term test, okay, still going to mean you diverge, period. There's no exception to that. But what if I pass the nth term test? What if I can show that my terms are approaching zero? Let's consider the following. This is the alternating harmonic series. The alternating harmonic series, according to what we just said, the value of this entire sum has to be smaller than 1. Why? Because the terms are getting smaller, and I just showed if the terms are getting smaller and, of course, approaching 0, then I'm bounded between 0 and the first term. That means that this is going to converge. Whoa. Now, turns out this is really, really cool. I can actually tell you what this converges to. I can't prove it today. I'm going to prove it in a couple of days, but just keep in the back of your mind. The infinite sum, when I added all the terms, we said it was real slow moving, but eventually it got infinitely large. Now that I'm canceling left and right, it turns out this sum here is equal to the natural log of 2, which is completely insane. Natural log of 2 is about 0.69. I'm going to be able to show that to you in a few days. We have a few more tools that we need to come up with, but it's very cool. This infinite alternating sum actually has a tiny, tiny finite amount. So if you just messed around with your calculator and you kept adding numbers, what you'd find is the sums are just getting, the kind of zeroing in as you go in. So here's how it works. I'm going to talk about all the different cases. So it's all about alternating series, okay? Now there's a term that we use. Okay, I'm going to give you a simple analogy. When you were a senior in high school and you were applying, let's say, to a 4-year school, probably in the fall, and then you got accepted. Awesome. You got accepted maybe in January or February. So of course, you didn't need to finish out that year, right? You could just stay home. You didn't even have to go to school. You could just go ahead and fail all of your classes because you got accepted into that school. That's how it works, right? Or if you failed your classes, would you be no longer accepted to that school? Yeah, that's probably how it works. I taught high school for several years, and we actually had an academic counselor who would tell the kids, once you're in, you're in. And we'd have more than half of the seniors every single year got rejected from the schools that got them in because they failed classes. No, your acceptance is conditional. There's no such thing as an unconditional acceptance for a high school senior into the school. It's conditional on that you keep doing whatever it is that got you in. So if you got in because of the merit of your grades, then you got to keep the grades up. It's conditional. If you got in on an athletic scholarship, then it's conditional that you actually play the sport. You can't get in and say, no, I'm not going to play the sport now. And then scholarship's revoked. The idea is, if a condition is met, then the conclusion will be. So we have a type of convergence that we call conditional convergence.
Absolute value test?
No, not exactly. It's actually simpler than this, okay? So let's suppose that, let's start with something simple. I've got some alternating series, and again, it doesn't matter if it's -1 to the n or -1 to the n minus 1. If it's -1 to the n, it just means it's going to add up to the opposite sign that -1 to the n minus 1 would have added, because you factored out a -1. That's irrelevant on convergence, okay? Okay, here's the problem, okay? If this diverges, we're not out of the woods. We know the harmonic series diverged. If this diverges and, let's say it, I was going to say you don't pass, it passes, and it passes the nth term test. I have a divergent series, but it passes the nth term test. Well, we know the nth term test is not a condition for convergence. We know failing the nth term test is a condition for divergence. But I have an alternating series. So if my alternating series, if this guy diverges but passes the nth term test, then the alternating series converges, and the word we use is conditionally. We get what's called conditional convergence because the original series didn't converge. But if I throw in the condition that it alternates, now it will converge. So I can have a series, I can have it diverge, but then have the alternating version of it converge. And that's kind of what today is all about. Now, there's a couple of what ifs. Okay. So first of all, what if this guy converges? What if my original series converged? Now I'm going to make it alternate. Anybody want to tell me what's likely to happen? I have a series and it converged, and now it alternates. Is it still
Converges faster?
It converges faster to a much, much smaller value. Does that make sense? It already converged. Now I just wiped off most of the terms by having them all cancel. So it converges even faster, like you said. So we say, if this converges, then this guy, we use a different word. We say it converges.
Absolutely.
Absolutely. Now, I always have fun with that one. So are you going to the store today? Oh, absolutely. That's not what we mean. That's a really solid yes. When you know, do we sometimes answer a yes or no question with the word absolutely? Are you going? Oh, absolutely.
Absolutely.
Absolutely, we do that. No, that's a completely incorrect use of the word absolutely in the English language. The answer was yes. No, absolutely. Have fun. Does it converge? Oh, absolutely, it converges. No, that's not what we mean. We mean that in this series here, they're alternating. This series here would be the equivalent of taking the absolute value of every one of these guys. In other words, the non-alternating series would be the equivalent of taking the absolute value, because then there would be no more negative ones. So if I take my alternating series and instead make it non-alternating, that's equivalent to taking the absolute value of every term. If that one converges, then we say this one converges absolutely, like as an absolute value, absolutely. Not it really converges, you know. Okay. And there's one more case. What haven't we looked at yet? We've converged conditionally and we've converged absolutely.
Diverges without limit.
How do I diverge? Yeah, how can I diverge? And by the way, all divergence would have to be without limit because of the alternating nature, kind of like an evil geometric series. So there is one more case. Okay, let's go back. This guy diverges, okay. And it fails the nth term test. Well, failing the nth term test, I automatically was going to diverge anyway. Okay, so if I have an alternating series that fails the nth term test, I'm still going to get divergence. But the worst one is I'm going to get divergence without limit. Right now, divergence is good enough. So there's three possibilities on an alternating series: converge absolutely, converge conditionally, diverges. And by the way, you don't put a condition on the divergence, it just diverges. That's it. So we're going to do examples of each one. Okay. And I'm going to walk you through, because there is a way of doing this, and we want to make sure we're doing it correctly. This is not one of these you want to get creative. I'm gonna show convergence my way. No, you pretty much have to do it the same way. So let's look at a few cases. The trickiest one is actually the divergence case, by the way. So let's consider the following. Let's consider n equals 1 to infinity of let's say n over n cubed plus 1, 2 to the n. Sorry, I need a negative 1 to the n, and then n on top. Yikes, this is very busy. Now, it is not possible to test an alternating series. You can only test the non-alternating series. So the next thing we're going to do is set up the problem that we are going to actually attack. And we start by, we write consider, and I'm going to write the same thing, but the non-alternating version. Consider this series right here. Now, either this series converges or this series diverges. It's one or the other. If this series converges, I'm done. There's nothing left to do. If this series diverges, then I will try the nth term test to see if I can go a step further. Okay. Now, what do you want to do on this guy? There's multiple things I could do. There's actually a whole bunch of different tests I could do. I could do a direct comparison. I could do a limit comparison. I can do a ratio. I can do a root. I can do almost everything because I've mixed things.
You only have to use the root because of 2 to the power of n.
But you could also use ratio. How about we just do a direct comparison? Look at the denominator. It's going to get huge. I'm going to do a direct comparison because I'm lazy.
No, that's too easy. You can't do that.
How about I compare this one to this? A what? Convergent P series. You're going to like this. I'm going to compare it to this one. Now, 0 is smaller than n over n cubed plus 1 to the times 2 to the n. Heck, if the 2 to the n wasn't there, this is already smaller than 1 over n squared. But I also threw an exponential function in the denominator. So this is really smaller than this guy. This guy's way smaller than this guy, yet positive. Right? So what can I say with certainty? I can say this series converges by the direct comparison test. Okay, everybody cool with that? The non-alternating series converged by the direct comparison test.
Wait, so if it's so if it's less than 1 over n to the second power, we know it converges if p is greater than 1. How did you figure if
What's B? I don't know what that
EP
means.
as a P series? The P
Oh,
and P
I'm
series.
sorry. I said B. I'm like, I don't know. We know that's a convergent P series, and this term by term is significantly smaller than this.
But what if well I'm saying because if you compare it to another P series.
Well, this isn't a P series because I got that 2 to the n. That's why I did a direct comparison, because my denominator here is growing without bound. In addition to the fact that n over n cubed plus 1 is already smaller than 1 over n squared. But this is not without question. This is actually trivial.
Let me ask you this.
This
Let me
is
ask you
tiny.
this.
Yeah.
Let me ask you this. Which is smaller, 1 over n or 1 over n squared?
Which is smaller?
Yeah,
1 over n,
squared.
the sum of 1 over n diverges, the sum of 1 over n squared converges. So
Okay.
as the P series, remember, if that's bigger than 1, then the P series converges.
All right, got it. Sorry.
You might have been switching those in your head. Now, we have not even touched the alternating series. You agree? We have not even looked at the alternating series. Everything we've said is about the non-alternating. And we just proved the non-alternating diverges. Do we have to do anything else, or are we done?
We're good. We're done.
So
Probably
what-
have to write that it converges absolute.
Beautiful. Converges absolutely. By the way, it does not converge absolutely by anything else. If I write one more word, anything that I say will be absolutely incorrect, and I will nullify everything I just said. There is no such thing as a test on an alternating series. The most common wrong answer I get from every Cal 2 student who's ever lived is it converges or diverges or whatever, blah, 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 by the alternating series test. That's my favorite one. I've helped co-author 6 different calculus books. Please explain to me what the alternating series test is, because there is no such thing. Yet that's the number one answer I get to every single problem when students have no idea what it is. There's no such thing because you cannot test an alternating series. You test the non-alternating series and you make your conclusion about. So this isn't by any reason. The reason applied to here, and because the non-alternating converge, the alternating converge absolutely. That's it, done. Finito, go home. That's it. Now, all of the work is always going to be on the non-alternating. So let's do the next example. Let's do one where it wasn't quite so pretty. Oh, that was kind of ugly. Okay, I admit that wasn't the easiest looking one. Let's do one. Let's say n is 1 to infinity of, how about, let's see, not so terrible. -1 to the n over n plus 2. Now that's just not very complicated. So we start, you don't take absolute values, you just start with the non-alternating series. So the first thing we're going to write is consider 1 over n plus 2. That's the non-alternating series. Now, do you believe this series converges or diverges? Anybody?
Diverges.
Because it looks like what series?
Harmonic.
It looks harmonic. Yeah, that makes it fairly simple. Now, the problem is because it's n plus 2, I cannot do a direct comparison because it's just a little bit smaller than the harmonic, but I can easily do a limit comparison. You all agree with that? Limit comparison, piece of cake. So we will compare to now, I do want to remind you, most of you guys have been pretty good about this. Occasionally this following thing happens. I'm going to take this infinite sum. Watch what I'm about to do. I'm going to take this infinite sum and compare it to 1 over n. Does anybody have a problem with that?
Yes, it is not an infinite sum. It's just a
Yeah, this
1
is
over n.
one term, so it's all, this automatically converges no matter what because it's just one term. I can't compare the infinite sum to a single term. Now, the intent is kind of, oh, I meant the series, but you kind of need to make the distinction between one term and an infinite sum. They're really not the same thing. Okay, now we're going to do a limit comparison test. So the limit as n goes to infinity, 1 over n plus 1 over 1 over n. So I can do that.
Times n.
I'm lazy. And you guys, hopefully, in looking at your work, most of you did that. So you said this is this, and what is that? That limit is
1.
1.
now. A couple of folks on the last quiz had some issues. Go, oh, wait, I need that to be bigger than 1, or do I need that to be smaller than 1? If you're doing a limit comparison and you're actually considering the value you get to make your conclusion, then it just became an absolute guess.
Is it n plus 1 or n plus 2?
I was about to say, it's just a small mistake, right? Yeah, just
Sorry, 2. That guy there, are you looking, is it bigger than 1, smaller than 1? Is it positive? Is it negative? If you're looking at the actual value, you're going to make the incorrect conclusion at least half the time because it means you're making, no, what am I looking for? That number has to be finite.
Non-zero.
and Not 0. Positive, negative, large, small, completely irrelevant. I actually had more than one person when they did their limit and the number is greater than 1, therefore. Because if it were less than 1, does that mean you would make the opposite conclusion? And remember, since it never matters which one you put on top, any limit that gives you greater than 1, if you switch what's on top, would now be less than 1. And yeah, no. Finite non-zero. That means that these two have the exact same behavior in a sense. Okay, so now what do I know? I absolutely know that this, okay, this guy diverges by the limit comparison test. Okay, we tested the non-alternating series. Oh darn, it diverged. Am I done? No, because of the alternating nature, I can still get conditional convergence. What do I have to do to get conditional convergence? Do you remember? The nth term test has two parts. The first part is that the limit, this is the more important of the two, by the way, the limit as n goes to infinity of an is in
Equals zero.
fact 0. And the second part, I'll put up here, is that 1 over, now what's the next term? I'll write it like this. 1 over n plus 1 plus 2 is smaller than 1 over n plus 2. Is this a true statement? Is the next term always going to be smaller?
But we
Yes.
have to test it.
Yes.
Yeah, that's actually for all n greater than or equal to 1. That's the second piece. This is lesser of the two. This is the more important. If this passes, it would be really, really difficult for this to pass and this to fail. So that's why a lot of times I don't, yes, technically you're supposed to do them both. You are supposed to do them both. But if this passes, this is almost redundant. It's really hard for this one to fail. If my terms are approaching 0, how could they not be getting smaller? Does that make sense? So what does that mean? I just passed the nth term test. I have an alternating series that the non-alternating diverged, but it passed the nth term test. That means I met the condition for conditional convergence. So this converges conditionally. Ah, that's why we like the alternating. My original, this guy here would diverge, yet by alternating, I got convergence. So there's a whole bunch of series out there where you've been saying divergent, that if I put that -1 to a power in front, I might now get convergence where I didn't otherwise. Now, remember, if your original series converged, now if you make it alternate, it's going to converge faster to a smaller number. That's not even an issue. That's a piece of cake. Okay. It's this guy, things that are like a harmonic series. Now we love that one. We're going to just do my eraser. Here we go. Now let's do another one. I'm going to show you the one that gives us the most trouble, of course, would be something that diverges, but you're going to like this. Hold on a second. I had another blue pen. I don't know where it ended up. It's starting to run out of juice. Here we go. All right. Oops, sorry. Meant to do -3. I'm sorry. Okay. Don't love this one, or do we?
You just factor out
Well, first of all, we'll consider this. Now I have two viable options to work on this one. What are they?
You forgot the negative, by the way.
no, that's the
No, he didn't.
No,
Oh, wait. Yeah,
It's
okay.
impossible to proceed on this problem. I can only proceed on that one. Kind of a theme. This is the non-alternating. There's two routes I can take, two tests I can use. What are they?
Would it be
It's roots,
direct
right?
comparison test?
root test.
Or
Direct comparison test.
Ratio?
No.
ratio.
Wouldn't you?
Ratio?
How do you know?
Whenever I see something to the
Because-
power of n, I do root.
It's because you see an exponential function. It's not the end of the denominator. You see an exponential function, so you can do ratio or root tests. The beautiful thing about ratio and root tests, when I do it correctly, I take a limit of a bunch of stuff in a ratio test. There's more algebra, and I get a certain number that acts like the R of the geometric series. When I do the root test, I write specifically something to a power, and I figure out what the R is. It's the same R, therefore the same conclusion. And I'm looking for an R that is smaller than 1 in absolute value. So what do you guys want to do? Ratio or root? It matters not.
Root.
Okay, we'll do root.
Yeah.
So the first thing, before I do root, I now have to rewrite this. And what do I mean by rewrite it? I have to rewrite it so that it looks like that. Well, pretty sure there's a 3 on top. What's on the bottom?
Two n.
Is it an N? It's that guy
One
there.
over.
Square root of n.
The 1 over n.
End of the one.
Yeah.
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 It's kind of ugly, but we know
The
its
one.
limit.
It's
We
not
don't
the
have to
same.
prove its limit. We
1
know
over.
its limit.
Oh,
Okay, I now have it of the form. So now all I gotta do is take the limit of that guy right there. Okay, so the limit as n goes to infinity of 3 over 2n to the 1 over n. I'm gonna rewrite that as 3/2 times the limit, because that guy right there just looks a little bit disconcerting to me. That might make it easier. We proved this limit. You never have to prove it again. What is that limit? Is one you might even want to write down, because you can use that on the next test, I hope. What is that limit? The limit is n goes to infinity of n to the 1 over n. You remember?
0?
No,
No.
one.
it's 1. So that
Oh,
means
1.
this is 3/2. Now I did a root test. If we had done the ratio test, here's my money back ironclad guarantee. If we had done this problem using the ratio test, we would have got the same 3/2. It would have been impossible to get a different number. That's where we would have taken the n plus first term over the nth term, taken the limit, done all that good stuff. Now, algebraically, that one probably had more steps, but this step here does trouble some people, so it didn't matter. That's when it matters. I just did a test where we're comparing it to a geometric series. So I'm saying this acts like a geometric series with an R of 3/2. Tell me about that.
Can I ask a stupid question?
Oh, please.
Is infinity to the 0 power 1?
Well, something approaching infinity to the 0th power. Yes.
Oh, so that's why we get 1 right there,
Well,
right?
we got 1 because we actually did this limit, if you remember.
Yeah.
We did it like this. We did the e to the log thing. And then we did it that way to prove it. But once we proved it once, I said, you can now use that as a fact forever. Okay.
Okay.
The problem is it's not an indeterminate form. So it's one of those weird ones that comes up just often enough that we're not always sure what to do. And it's not an indeterminate form. So I can't really do L'Hopital. There's a few things we're not really sure. But this form comes up basically, and whenever you use the root test, this is likely to come up. That's why I wanted to show you guys ahead of time. I don't want you to have to calculate this limit every single time. We're treating that now as an identity. It's a fact. I wouldn't say formula, because it's one number, and that's what it is. It's beautiful. Now, what does this mean? This means that this series what?
Convergence.
Say again, I couldn't hear. Converge.
Diverges.
Diverges by, and we did the nth root test. So now what? Now I got to do the whole nth. Nope, you're done. We are. If my ratio is 3/2 in simple English, doesn't that mean each term is bigger as we go? Aren't my terms getting bigger? That's why the ratio was 3/2. Oh, I don't have to do the nth term test. It already failed. Well, we didn't do an nth term test. Yeah, we did. In a ratio test, your limit is still the nth. You're still saying, what's the limit as I move on? Are my terms approaching 0, or are they growing without bound? My terms are growing without bound. Each one is acting like it's 1.5 times as big as the one before it. Every term is getting bigger as I go. So this simply diverges, and you're going to like this. Whenever you fail, what I mean by failing is you get divergence. When you fail the nth root or the ratio test, because your value is bigger than 1, you diverge. There is nothing left to perform, whether it's an alternating series or not. If you have, think geometric for a moment. I have a geometric series where the R is bigger than 1. That means they're getting infinitely large. Can't converge. If they're alternating, it's even worse. Then it diverges without limit. So the only time you actually have to even try for conditional convergence is if you did a limit or some sort of limit comparison or direct comparison or integral test. If you're doing ratio or root test, you never have to check for conditional convergence because it's not possible. Failing a ratio or root test means your terms are getting bigger. And getting bigger means you would fail the nth term test. So that extra condition of having to take the limit and see if it's zero only applies if you used a comparison test. So you're actually off the hook for a lot of work in these cases. Okay, so let's do a few more because I want you to get comfortable with this. All right. Okay, don't have a lot of choices on this one. What test?
One second, I'll get it to you.
Root?
Oh,
Or sorry, ratio.
Ratio, because
Ratio test.
factorial.
Ratio test.
Factorial can only be ratio. Yeah, and this is just from repetition. You go, yeah, it's all about categorizing. That has to be ratio. The previous problem could be ratio or root. And now that's just a preference. Which one do you feel more comfortable performing? That's it. It's actually that simple. So I'm going to use a ratio test. So we're going to take the limit as n goes to infinity, okay, of n plus 1 to the 6th power over n plus 1 factorial divided by this quantity. So I'll say times the reciprocal. And everything's an absolute value, but since none of those can be negative, I can drop the absolute value in the next step. Now, I really want to cancel some stuff. Can I cancel anything?
sure.
Well, let's start with this guy. I'm a big fan of just writing right there. N plus 1 quantity factorial.
It's n plus 1 times n factorial.
Beautiful. Somebody has been practicing. Then, by the way, don't go any further because it's perfect. Could I do anything with those guys if necessary?
I mean,
Well, we
n
can-
plus 1's the 6 over n plus 1.
Could I go like this and make that a 5th power? Is that legal?
Yep.
That might not be a bad idea. In fact, and then I can go like this. Ooh. All that really matters is that when I write my next limit, I don't have any more factorials. Factorials, you cannot take the limit of a factorial, so I need to get them out of the picture here. So what do I have left now? I have an n plus 1 to the 5th power on top, and I have an n to the 6th power on the bottom. Are we good on that? Does everybody agree?
Yep.
Now what? I can L'Hopital it 5 times. All right.
Just you have an n to the 5th over n to the 6th as the leading terms.
Therefore, my limit is
Infinity.
0.
ooh, which is it?
It's 0.
0.
Numerator smaller than the denominator, so the limit is 0. That's important. By the way, I can do everything right, but if I get that number wrong, it's going to change my conclusion, and that's kind of a bummer. Now what? I did a ratio test. So what should the next thing I write? There's 2 more symbols I need to write. This is a ratio test.
Less than.
Less than 1.
Less than. Very specifically, what are you always comparing it to on a ratio or root test? 1. That, by the way, that is important because I'm using a ratio test. I calculate the limit, it is less than 1. The fact that it's 0 is not important. The fact that it's less than 1, meaning this series what? Finish the conclusion for me.
Convergence by a ratio test.
Perfect. This, by the way, I can't make my conclusion on this one until I finish my conclusion on this one. This one converges by the ratio test. You didn't perform the ratio test on this one. You performed the ratio test on this one. Therefore, what's the conclusion to the original problem?
Converges
Converges
absolutely.
absolute.
Converges absolutely. Perfect. Converges absolutely, and that's it. Not by any other reason, because this converged by the ratio test, this converges absolutely. Okay, does that make sense so far? Oh, okay, it's kind of cool. Did I have to do extra work because this was alternating? Not really. I did the non-alternating, it converged, so I'm done. If this guy had diverged and I used the ratio test, if this guy had diverged, then I would still be done and I'd have this one diverging. And you like that because the ratio test is going to be the most common test you perform. So if you converge by the ratio test, then your alternating converges absolutely. If you diverge by the ratio test, then your alternating is going to diverge. It's only when you're doing a comparison test of some sort that you have to even have the possibility of conditional, like the harmonic series, for example. So let's do another one. If you notice, I mentioned this at the beginning of class, today is going to feel almost like a review in that we're not learning a new technique. We're applying all of our techniques at once. The only additional thing I'm doing is I'm saying, hey, now let's let them alternate and see what happens. But we're still doing all of the same tests. So we get some additional practice in a more of a bigger picture kind of situation, right? Let's do one, excuse me. Let's say n equals 1 to infinity, -1 to the n times n plus 1 over 2n squared minus 3n plus 7. Something kind of. All right.
Limit comparison test.
Eventually, yes. I think that's probably the way we go. So we start by, we don't write anything to do with this until we get to the conclusion. This, we're going to write our conclusion. And we have three possibilities. This is going to converge absolutely. It's going to converge conditionally. It's going to diverge. Everything I do over here is how I'm going to make that conclusion. Okay, hopefully that's clear. I don't do anything else to the left side. So I start by saying, let's consider the non-alternating. And so you want to compare it to what? Now, here's how
1
how
over
you make
n.
the decision.
Hmm?
Most of you are doing a really good job on this. You're not thinking too much. How do I make my decision? What am I looking at?
The difference of the power of the leading terms.
Yeah, I'm looking at the degree difference. And right now the degree difference is what?
1.
1. So therefore I want to do basically a P series with an exponent of 1, which of course would be the harmonic, compared to, hopefully that is not something that is taxing. Does it matter how big these exponents are? No, I just look at the degree difference of the leading terms. That's it. Because then when I do my limit comparison, I'm always going to get a happy constant if I did it right. Right? I'm going to compare to this. We'll definitely use the limit comparison. And the reason is real simple. With that 2 on the bottom, term by term, these are smaller than these. So my inequality is in the wrong direction to do a direct comparison. If that 2 had been on top instead, oh no, then I would definitely do a direct comparison. That'd be a piece of cake. So I'm going to compare to this guy. Now remember, it never matters which one's on top. But do you remember the suggestion I made? You can take
Complicated on top.
Well, not just leave it alone. I said, take the original, make that the top. And the only reason is you can do this divided by this. But then when I flip it over, is it possible I could miswrite it when I'm flipping it over? Because it's not going to look the same. It'll look like the reciprocal. I may not recognize if I changed the sign or dropped a coefficient. So yes, it's the more complicated of the two, the original. It never matters which one goes on top. But I find it easier if I go this way, because then I don't have to change that at all. I'm much less likely to miscopy it. That's why I like to put that one on top. It's not a rule. It's just a way to make sure you're not messing it up. There is no absolute value here because that ratio, that limit does not have to be any particular sign. It just is. So when I do this, I'm going to get n squared plus 2n on top, 2n squared minus 3n plus 7 on the bottom, and that limit is
1/2.
1/2. If you are not getting a happy constant there, it means we messed up with the exponent somewhere. Remember, 0 and infinity are not possible results. 0 infinity means I messed up my exponents. Now, if I had done the ratio the other way, I would have gotten 2. Do you agree? If I put the 1 over n on top, I would have gotten a 2. So therefore, if I'm comparing this number to 1, that is a grave error.
No, we
Because
just
the
need
other
a-
way would have been 2.
How did you get 2n right there instead of just n?
How did I get 2n?
It's n multiplied by
Yeah,
the
you just
numerator.
multiplied it.
Oh, I'm sorry.
n
That's
Yeah, it's
n
just-
times
That's it.
1 is
Yeah.
okay.
I'm sorry. I thought you were talking about that guy.
No, no, no.
No,
Yeah.
you're good. Thank you. Yeah,
Okay.
yeah, when you're at the board, you have tunnel vision. So I'm looking at this, and again, I want to remind you, had I gone the other way, had I put this guy on top, do you all agree that I would have been taking this limit? Does everybody see that? And then I would have gotten 2. Both of them are finite, both of them are non-zero, both of them are perfect. What this means is that this series is acting like it's about half as big as this. The 2 would mean that this series is acting like it's twice as big as this. That's the same thing. But here's the problem. If I'm thinking ratio or root test, then it means I'm thinking that I'm going to compare to the number 1. Do you see the problem with that? This is less than 1 and this is greater than 1. I'm not comparing it to 1. This isn't a ratio or root test. There is no ratio here. I'm never comparing it to 1. I'm just saying, is my limit finite and non-zero? The ratio or root test is the one that acts like a geometric series. That's why we're comparing it to 1. That is not even close to what this is. So this is a huge error that some people do. Or the other one I see people go, well, it's greater than 0, therefore. Why would you be comparing it to 0? There is no series that we compare to 0.
Well, Professor, what I have done in the quiz and what I have done in my practice problems, I would say it's a constant, and therefore, if this limit converges, the other one converges.
Yeah.
I state that it's a constant. Is that correct, or?
Yeah, it's a non-zero constant.
Okay.
What if I got 0? If I got 0, it would have meant that the numerator had a smaller degree than the denominator. And after I perform this, it means I would have been comparing it to the wrong thing. That's what that would mean. If I got infinity, that meant the numerator was bigger, which again meant I compared it. When you're doing a limit comparison, it's almost like you know the answer to the question at the
Yeah,
beginning.
like I can look at this and I can tell you it's 1/2 of just with looking at the problem.
You know that when you do the right comparison, the right test, and you set it up, you know you're going to get a finite limit, and that's a good thing. Do you agree? That's a good thing.
Yeah.
And so therefore, but remember, you're leaving an instruction manual for the next person. Don't do them both. Just do one. We did the top one. Now, what did I just say? What is my conclusion at this point in the problem? At this point in the problem, we've got this series. So we're not out of the woods yet. There's a lot.
You never stated that you're comparing it to a harmonic
Oh,
series.
thank you. Yes. Compared to this, we said it out loud. We didn't write it. We want to write it. A divergent harmonic series. Beautiful, beautiful catch. Why does that matter? Why does that matter? Because that word right there tells me what this is going to do. I can't have a conclusion here that is different from this. Does everybody get that? If I'm comparing it to a convergent series, I can't get a conclusion of divergence. If I'm comparing to a divergent series, can't get a conclusion of convergence. Okay, so that means that if I choose the right thing to compare it to and I get a successful, nice, happy number there, now I can absolutely say this guy does what?
Does the same, which converge.
So,
Oh, is that diverge? Yeah.
by what test?
Limit
It'll
control
list.
test.
And
Limit.
by the way, you always state your test because this is your rationale. Now, am I done with the problem? No,
No.
I'm not. I still can get conditional convergence. I can still get conditional convergence. Okay. And I said, I'm going to let you off the hook and just ask for the limit of 0. So what am I taking the limit of? I'm going to take the limit of that, not the sum, that individual term.
You said the limit of 0. I believe you meant a limit of infinity.
I'm sorry, say again.
You said limit of 0.
I need to get the
And-
limit
I mean,
to be 0.
Yes.
So what is this limit? I said, as opposed to doing the, just getting the limit is 0. I said, you don't have to really do the second part. Showing
This
the
is
limit
0.
smaller. Is this 0?
Yeah.
Yes.
So in English, we said I have an alternating series where the non-alternating is diverging, but the terms are approaching 0. That's all I needed to get what?
Converges absolutely.
No, not absolutely.
No, conditionally, because this one diverges.
No, my bad.
Oh, yeah, it's so bad. That's like timeout worthy. That's
Yeah,
close to the deduction miles.
take out miles. That's what I was gonna say.
Yeah, that's, although some of you guys don't have any, you have to borrow from each other. By the way, you are allowed to borrow and you can be charged interest on your miles. I don't know how that works exactly. You know, get a mileage calculator. So this is all the work. We hated this because that means I got to do one more step, but the one more step is this. The one more step is like the easiest step there is. That step's never going to be hard ever, right? Because you're taking the limit of a rational function. That's a piece of cake, right? Let's do another, shall we? Yeah, I want you to have this feeling like I got these. Man, these are so nice. Now I'm gonna throw a weird one at you. All right, I've got 3n to the 4th minus 6n squared over 2n cubed plus 5n plus 1. And I'll put the -1 here. All right. -1 to the n times all of this gobbledygook. All right. Every now and then we can just get lucky. So first thing I'm going to write is consider. The reason I write consider is this is the only problem we're now looking at. Okay, now what?
I do the same thing. We just
Can't
did
you
in the last
just
one.
immediately look at it and say
Yeah.
this doesn't pass the nth term test?
So very specifically, what do you want to do?
Take the limit as n approaches infinity.
Remember, I just said every now and then you just get lucky. What is that one?
Is that called the divergence test?
Nth term test, yeah.
And
So-
I've been calling it divergence.
Well, here's the problem. Every single test you ever perform, integral test, limit comparison, direct comparison, ratio, root tests are all tests for both convergence and divergence. So every time you came up with the conclusion of divergence, it's because of that test. That's why when you say a test for divergence, it's kind of vague because the 5 main tests are also tests for divergence. So most authors will just call this the nth term test because I'm taking the limit of the nth term and it's either 0 or it's not. By the way, what's this limit?
Infinity.
Yeah, I think that misses 0. I'm gonna put, and that's not 0. I think that misses 0 about as badly as you can miss. So
Plus or minus.
here's the best part about this problem. We're done.
It's done.
We diverge. That's it. So I said every now and then you get lucky. That's not the norm. But if you saw something and you clearly identified, these terms are getting bigger, they're not getting smaller, that's equivalent to failing the ratio test. Because failing the ratio test means your terms are getting bigger. So if I asked that question, I would be thrilled if you got through this with just, do that and walk away, because it means you're looking for the right thing. You're not doing the nth term test on every problem, but when you look at a problem and go, hey, those aren't getting smaller, those are getting bigger, I'm done. Take advantage of that every time. Does it happen very often? No, but there's probably a couple of problems in every section where the author will sneak one of those in on you just to see if you're paying attention. One of my favorite questions that I would ask in Calc 1, by the way, this is a Calc 1 question I used to love to ask.
That's not cool.
Seriously.
Oh, God, I hate cotangents. And, by the way, what's the answer?
Yeah.
1.
Tangent squared. Oh, 1.
It has to be that fast for all human beings in a calculus class because these are reciprocals and you differentiate. But I'll ask this question and I get this or something else that's really long-winded in a whole page where probably it's not even ballpark. I'll say, guys, sometimes you gotta just be paying attention. These are reciprocals. So you're differentiating one, which is 0. You say, that's mean. No, it's not. When baby algebra, when we were working on exponents and we were learning all of the rules of exponents, remember, okay, when you're multiplying things with the same base, you add exponents, and when you raise it to a power. And so you had stuff like this, x to the 6th, y to the -3rd over x to the -4th, y to the 5th. Oh gosh. And I'm going to raise it to a power. I would do stuff like this. And I'd be able to do all this manipulation. By the way, what's the answer?
1.
1.
Yeah. I'm seeing, do you guys actually understand what an exponent is?
So you're not saying you're gonna have something like this on the exam, but you're not saying you're not having
Well,
something
no,
like
it's
this on the exam.
the thing like this, I would hope that you recognize right away and going, hey, you know what? I'm good to go. Now, few and far between, and here's the reason. It's not because, well, no one's going to try to trick you. No, it just, in the situations that we're doing, when you see polynomials involved, the situations that are creating these problems in the first place, you're generally going to be seeing smaller degrees on top because where the problems came from, they all come from someplace, not all off the top of my head. I mean, they actually do have application that come from somewhere. And the fact that they're coming from somewhere, you're going to have a smaller degree on top pretty much every time, but you still might have divergence. So today, our goal is to take an alternating series and then examine the non-alternating using only things we already know. I did not teach you a single new technique today, only things we already know, but now it's all of them sort of lumped together. So I have to make that conclusion. Ratio test, limit comparisons. Which one is this? I finish, and now I make my conclusion about the alternating. That's great. This is the end of the material because tomorrow everything's going to change, but in a good way, in that today the question was, here's the question we did today. Maybe it was, I don't know, n squared over, 2 to the n and converge or diverge. And you go, okay, that's pretty easy. I'll do that problem all the way through. Tomorrow, that's the only difference between today and tomorrow. So what's
Oh, that's all.
Is tomorrow's material going to be on exam 2?
Anybody want to answer that one? I've only addressed
Nope.
it 5 times today and yesterday. And come on, you know the answer to that question. What's the answer to that question? What's the answer to that question? Where are we? Where are we? We're right here.
Yes.
What does
Power
that mean?
series?
That's today. Okay, that's today. So tomorrow we start, what if I throw a variable in there? Does that change things? Yeah, because guess what's no longer going to be a thing? Divergence. There's gonna be no more divergence series ever again. The moment I throw a variable in there, you can't get divergence anymore. See, because x could be 0. Oh, so the question will now be, regardless of what this did, when I throw the x in there, for what values of x will it converge? And that's the part that we now use to answer questions. We did all of the work to figure out how to determine convergence or divergence of a series, so that starting tomorrow, when we throw variables in there, which is actually the general thing, then we'd know, oh, okay, as long as x is between here and here, it's going to converge, and everything else it will diverge, kind of thing. But every series will be able to converge now, at least somewhere. And that's a big picture goal. But that's where the really cool stuff comes from. All right.